Yeah,
We're live.
Hi, everyone. Thank you for joining our session today. We are very happy to have all of you join. My name is Ngesa Marvin, and I'm also joined here with other amazing organizers, including Brian and Philomena. Philomena?
Hi everyone. Welcome to today's session. It's a pleasure to be here. Unfortunately, I will be unable to switch on my camera today. KPLZ decided to do their thing. Yeah. So, Brian.
Hi everyone, I hope you're having a great evening. This is the last Thursday of August, so I hope you are psyched up going to a new month. I'm also excited having you join us today. I really appreciate you making time to come and join us in this session. I hope you'll gain a lot from this, and I can't wait to listen to the different amazing things that we will cover today. Thank you very much.
Thank you, Brian. So, once again, welcome everyone. We're very happy to have all of you here. And just to confirm, Brian, can you see my screen?
Yes, I can see your screen.
Perfect. So, today we're going to take you through our week 3. Of course, we came from week 1 to week 2, and today we are on week 3. And on week 3 of this study jump, we're going to go into the introduction to deep learning. I hope all of you guys are excited as we are. On week 1, for the guys who are joining us for the very first time, we went through introduction to machine learning. We covered tools like pandas, matplotlib, scikit-learn, and on week 2, we went to intermediate machine learning and even did things like feature engineering. Today, we're going to go into introduction to deep learning, cover computer vision, and even SQL. So welcome, everyone. And in case you have any question, feel free to drop it on the chat. Feel free to tag us on Twitter. We'll be able to check all of them and answer all the questions. Of course, we're going to go through all this content, but at the end of it, we want all of you to finish what's on Kaggle, because we depend on Kaggle Learn for the content and even the certifications. And we want all of you at the end of it to receive a certification, and we'll guide you on how you can click and even get the certification. Today, we're going to cover things like neurons, things like deep neural network, what is stochastic gradient descent, how can you use it on your model, what's overfitting, what's underfitting, what does it even mean for machine learning, and how is it different for machine learning and deep learning? Are they different? Are they the same? We're going to check out on all that. We're also going to do computer vision, and particularly how to do image processing, of course, with convolution neural networks, and of course, with using Keras. We're also going to check what max pooling is, and even dive into SQL. So get ready for all this. And I'm also joined with this amazing facilitator. They've already introduced themselves, so I won't really spend much more time here. And of course, all this, we're doing it to get all of you ready for the Keras Community Day. We are going to have a Keras Community Day for Nairobi on the 30th of September. And all we're going to do is discuss deep learning and discuss mathematics and discuss how Keras abstract all the mathematics and allow you to focus on the main things when you're building your models. And even how today you can be able to use Keras as a user interface and have all these on automatic differentiators like TensorFlow, PyTorch, JAX, how you could switch them the way you'd want to switch them. But I don't really want to talk more into this. I know you guys are excited, so let us all dive into this. And now I'll hand it over to Philomena. Philomena.
Cool. Thanks, Marvin. Sharing my screen. Okay, cool. Yeah, so I'll just do a quick walkthrough through the intro to deep learning. Marvin will take you more in depth into actually what deep learning is and some of the examples. What is deep learning? So, if you'd like to get a deeper understanding or a more broad understanding of what deep learning is, the best way I'd say is to start with this. I don't know what to call it. I can't remember what they're called, where they're getting the circles against each other. But yeah, so deep learning is a subtopic of machine learning, and then machine learning is a subtopic of artificial intelligence. There's a lot of talk about what AI is, so I'll just start by maybe indulging you on what AI is. So, briefly, AI is just a simulation of human intelligence in machines, such that it enables them to perform tasks that more or less typically require human intelligence. So it enables it to behave or mimic the behavior of a human. And now, when you get into the inner circle machine learning, so machine learning is basically mostly focuses on creating algorithms that enable a computer or a machine to be able to learn from data and also improve on their task performance or enable it to perform different tasks without explicitly programming it on how to do it, such that it's able to learn from the data. Then deep learning, where you have it in the inner circle, is as it's kind of like a specialized form of machine learning that now involves neural networks. And so you work with multiple layers. That's why it's called deep neural networks. And then, so it's usually used in things like image recognition or um, NLP and the likes, such that um, it's able to learn from the data without being given the explicit features of the data, kind of like what we have in machine learning, which is, let me move to now this slide. So, which is what I would term as the main difference between deep learning and machine learning, such that when you are building a machine learning model, you'd find that you are the one who's dictating to the model which features it should focus on, and you're performing things like feature engineering. But now, when you're coming to deep learning, you pass in, let's say, an image, and then now it automatically through the layers learns the different types of variables from the image, so that it's able to, whether depending on the problem that you have at hand, if you want to maybe differentiate between a cat and a dog, then now it's able to learn what a cat looks like, what a dog looks like, as much as they both have noses, they both have fur and the likes. So it's able to look into the nitty-gritties of the image to be able to learn from it and be able to make a decision. So other differences and maybe characteristics of machine learning and deep learning are, um, so generally, machine learning mostly, more often than not, requires just a moderate amount of data, as long as it's spanning through and it's representative of the data set that you want it to learn and be able to, in the environment that you want it to perform on, it's able to learn from the data. But for deep learning, you'll find that you need a significant amount of data for you to actually enable your network to learn from the data and be able to make accurate results, accurate predictions of your data rather. Machine learning is more interpretable, such that you're able to have a clear understanding of how the decisions are made more often than not. Neural networks are more often than not described as black boxes, in that it becomes challenging at times to be able to understand how your model is actually working. But then there are some tools which we have, such as, I think it was called Deep Dream or something of the sort, that's able to enable you to know and understand your network, such that you know which features have been prioritized, and things like that. Yeah, so how neural networks learn from data. So it uses something called backpropagation, which will cover more in depth in in an image that we'll go through later on. So backpropagation is a method used to calculate the gradient of the loss function with respect to each weight by applying chain rule. I believe most of, if not all of us, at least have a math background and have interacted with chain rule at some point. So the process generally involves like three main steps. So we use the weighted sum, we use an activation function, and we have the output. So basically, a neural network has three layers: the input layer, and then we have the middle layers where the computation is done, and then we have the output layer. So through backpropagation, it calculates the area of the network's output, and then it distributes it back through the layers, adjusting its weights and biases accordingly, which I'll show you later on. So we also have the activation functions. So activation functions are usually used in through the middle layers of your neural networks, such that after you have been able to establish the weight and you've already passed in the input and you've multiplied and added your bias, then now the value that you have passes through an activation function, which is able to determine whether a neuron, which you'll go through later on, is fired or not. So you have different types of activation functions, which I'll go more in depth late in the later slides. So the two main activation functions that I have gotten a chance to interact with more in depth are the sigmoid function and the ReLU function. So the sigmoid function, it usually maps any input to a value between 0 and 1, mostly useful in binary prediction problems, such that it's an either or situation, like the cat or the dog. And then you have the ReLU, where the outputs of the input are directly if positive, input directly if positive, otherwise it inputs a 0 into your network. So what is a neuron, which we have been able to go through? I've been saying it a couple of times so far. So a neuron is um is basically the building block of a neural network. So that circle that you have in the middle, that you have like here and here and here, here and here. So it's the fundamental building blocks that mimics the behavior of a biological neuron in the human brain. So in this case, this problem, we're trying to determine whether if this is a circle. So this is the image that will pass into the neural network. And then at the end here, we have the output layer, which is either a triangle, a circle, or a square. So we're trying to determine whether it is going to be a square, it's going to be a circle, or it's going to be a triangle. So how this network works is what we had gone through before, the backpropagation. So we start from here. We have the pixels, which is 28 by 28, which is around 700 and something pixels, which are passed as individual inputs into this network. So this pixel, sorry, so this pixel here maybe is like this one. So each of them will have a representative of the input in the network here. And then now you are supposed now to multiply with the weight, which I have talked about before, which is now this 0.8, and then you add the bias, which is this B1. It's a representation of y is equals to mx plus c. And then now you pass it through the activation function, which now determines whether this neuron will be activated or not. If it has met the threshold, then it is activated. If it has not met the threshold, then it is not activated. And then now you get to the output, where you're able to measure, since now this is during the training. So you are, of course, when you're training, you're measuring it against a known output already for your model to be able to learn. So now if it is not mapping to the right, let's say maybe it mapped it to a square, then now it uses that error, and then now it does the back propagation as many times as you have defined it in your epoch, to to go back and learn again until and adjust. And now when it's going back through back propagation, it adjusts the weights and the bias until it gets to a point where it has ultimately learned well from the model, and it's able to make the right predictions in your data. So we have an overview of TensorFlow and Keras here, which, so basically, TensorFlow is an open source machine learning framework that facilitates the creation and training of machine learning and deep learning models. So basically, it makes your work easier, and it eases the process of doing all these things such that it sort of shortens that process for you. And then Keras is a high level API, which is now built on top of TensorFlow, such that TensorFlow is the backend that's being used for it right now. And so it simplifies the process of building now neural networks in deep learning, because it now provides the essential abstractions and building blocks. So I know most of you are familiar with how we build the machine learning models, and how um, more often than not, you'll find that you're spending most of your time in EDA and cleaning your data, and this feature engineering and feature selection. So when you are doing deep learning, it's a bit different, not too different, but a bit different. You'll find that you're spending around 20% of your time understanding and learning the problem, and most of your time collecting the data. As we said, like, if you want your deep learning model to perform well, you probably need a lot of data, and hence why you spend so much time in getting a data that's actually representative of what you would like your model, or in the environment that you'd like your network to perform in. And then you design your model. Evaluation and testing takes some time, because as you can see, the fact that it's shortened through building off of all these APIs and frameworks, now you would need to also go in depth in fine tuning it and trying out a couple of different things until it's able to suit your problem statement. Yeah, so I've just put here a couple of examples of how your model will look like, and you can see, like, it's pretty simple as compared to what you would have in a normal ML model. So you have a representation here of the linear regression, logistic regression, a neural network with just one single hidden layer, the middle layers that we were talking about. Here you can see it's using the ReLU as the activation function, and then the softmax and the dense and the last layer. Now you have the deep neural network, where you have more than one hidden layer in the middle, and this is just to give you a visual representation, or maybe just a visual understanding of how the code would look like in a normal setup. So what's usually similar in most of these networks is that your output layer will most often than not be dense. Whether you're dealing with a classification problem or a regression problem, or just a prediction, you'll find that you have the dense layer at the end. And these are just examples which you can be able to go through once we share the slides. Yeah, so training and evaluating the neural network. So I chose to go through this using an example. Just a simple example using the CFAR10 dataset, which is oftenly used alongside the MINST dataset, that when you're learning things to do with Keras and TensorFlow. So of course you start by loading your data set. We have the definition here of how your data set looks like. Then you normalize your data such that you reduce the bias that you have in your data by dividing by 255. And now you can see what we're talking about. So we have three layers, and then we have two max pooling layers to reduce the dimensions. So you have, this is the layer, it has the ReLU, then this is another ReLU, then this is another ReLU, and then now you have this layers in the middle to reduce the dimensionality in your data. And then of course you finish off with the dense layer to be able to now get to the output of your function. So this model is compiled using the Adam optimizer with a specific loss function tailored for integer classification. It's trained for 10 epochs. So the epochs is what we have here. which is you define the number of times you want the back propagation to happen in your data, such that when it gets to the finality of like to the final output, it's able to go back and learn and adjust the weights until it fits your data set and how you'd actually like to predict your data. So in this case, we've set it at 10, and you'll be able to see later on how it's changed over time and improved the performance of our network over time. Um, yeah, so this is just code for plotting it out to get a visual view of how your accuracy looks like. So as you can see, when we are starting out, our model was at an accuracy of 45.13%. And now that we were doing the 10 epochs, that's that it's going back and then going back again, adjusting the weights and the biases, it was able to improve its performance to around 78.44%. And so the training and validation loss decreases over the epochs, which is a good sign because it means the model's predictions are getting closer to the actual labels. But also there is a disadvantage to this, in that if you do this too many times, then you risk overfitting your data such that you are such that it learns too much about your data and it fits just the training data set that you have. And when you try to testing it out in other data sets, then you may find that it does not perform as well. So of course, it's good to make sure you look at your loss and your accuracy to make sure it does not get to that point. So other applications of deep learning in various domains. So we have image and video recognition, we have speech recognition, NLP, autonomous vehicles, game playing, healthcare. So like we have CNNs and RNNs, which are used in prediction of tasks and performing NLP tasks as well. Yeah, so TensorFlow and Keras are like the paintbrush and palette of the machine learning world. They equip us with the tools needed to turn raw data into beautiful, meaningful insights. I just wanted to end with that quote. And here there is a collab there that is I have attached in case you'd like to go through the notebook. And yeah, so thank you, and I hope you enjoyed and understood the session. I'll hand it over to Marvin.
Thank you very much, Philomena. Let me continue from where you've left. Screen. I hope you will. Okay. Where was I? Okay, I should be here. Can you guys see my screen? Yeah? I think probably you guys are muted.
Nope,
Yes.
we can't hear. You can, okay, sure.
I'm seeing the
Okay.
ML study jam intro to deep learning. Or is there
So full
another
screen,
screen
yeah?
you're sharing?
No, that's the one. All right. So thank you, Philomena, for the wonderful session. I'll take it from where you've left and talk about computer vision and try to link what you've talked about with computer vision and even with Keras. And I'm glad that you've been able to talk about Keras, talk about activation functions. I'm just going to build on top of what you've discussed. And of course, once again, my name is Marvin Ngasa, and I'm a device manager at Safaricom. I deal with a range of devices for IoT, and these devices collect different type of data. And some of them are structured, others are unstructured. The ones that are structured include devices for water meter, giving you information about how much water you can consume, and what are the alarms in these water meters, and also how much electricity you can consume. And some can even tell you the kind of vibrations that you have in your generators, so that if there is an anomaly, you can be able to detect from it. You can be able to do analysis on that data and detect that there's an anomaly that's going to happen in a generator. But a large part of this data is just structured. So the question is, what if you, I'll copyright slides. Okay, perfect. very important. So the question is, that's the one for structured data, but what if you go to the unstructured data? What if you have a camera on the street and this camera is collecting data from the street? Of course, most of the time we have these cameras on the streets of Nairobi and they can collect the feeds of how people are walking, the activities guys are doing, but they can't tell us what's happening in that environment. They can't tell us if someone is mugging someone. They can't tell us if some people are singing on the street. They can't tell us if a child is drowning. They're just giving us the feeds. And things like video, audio, and even images, they likely form the things that we call unstructured data. And of course, because they can't see all this, it's our work to ensure that we're able to build models that can enable these cameras to understand the videos they're collecting and even the images that they're having. So the one for all right. So the one for structured data, this is an example of those kind of devices. And this device here, it's a Kenyan-made dev kit. It's a Kenyan-made dev kit that has something called a microprocessor unit that can do addition, subtraction, division. Of course, some of them are from STM, others are from ESP. It also has a range of sensors that can collect temperature, humidity, and it also has the ability to collect all that information and send it somewhere in the cloud. And there's a way that you can represent it. You can see the bytes, how they're arranged, the one for latitude, the one for longitude. And since I've talked about temperature and humidity, you can see that on this structure or this payload definition, you can see that the temperature and humidity are on the 10th and 11th bytes of the 12-byte payload that we're having here. And that's the one for structured data. What about the ones for unstructured data? Probably I could show you some code before we go into this, since we are developers and we want to see some code. We don't just want to see people talking and talking. So let me show you something about images. Okay, let me reshare my screen. Let me know if you guys can see my screen. Share, I'll go here. Share entire screen. I think Brian should be here. Okay, let me know if you guys can see my screen. Brian, I'll be waiting for you to confirm for me. Hello, Brian. Okay. Okay. All right.
Yes, we can
So,
see it.
Perfect. All right. So this is the content for week 3, and I have an image somewhere here on this folder. Where they? Okay, perfect. Yeah, I have these 3 images here. One is for a stop sign, another one is for the image I usually use for events, and the other one is colored. In fact, I also have them somewhere here on my desktop. There's this colored, this online, and this one for stop sign. And I just want to open this, for example. We see the properties of the photo. You could see, where is it? Here, that these are the dimensions for the image. So I'm going to upload it, and then we try to do some things with it as we're trying to understand what convolution is and what computer vision is. So maybe we start from this point where we can see what do we have in an image. So these are the dimensions of the image. You can see 1280 by 1280. And then I'm going to go back to here. Of course, I'm going to use NumPy library, matplotlib, tabulate to draw for me a table for the images. And then I'll upload. I'll get a path for the image, then get the image, then I'll plot it here with matplotlib. After plotting it, I want to check on the height and width of my image, and you can see this is the height and width of my image. I can also calculate the pixels by multiplying the width and height of that image. Then I'll have this result here at the end of it. Then I also want to add all this into my slides so that I can show you how you can convert an image into a matrix of numbers, and how you can even add that matrix of numbers as a table on a slide, for example. Ideally, just to show you that all the images you see, you can actually represent it as numbers, or as a matrix of numbers. And I don't want to add 1280 by 1280 rows, a table of 1280 by 1280 rows in my slide. And therefore, I'm going to resize that image and add a table of 6 by 6 into my slide. So I'm doing some resizing here. You can see 6 by 6, the image that you have. Then if I print it, this is now the new image that I have from the first one. Of course, this is what's happening. My hands, okay. Of course, this is the first image. Then now this is what we are having. And then I also want to convert all those pixels into a table that I can add on my document. And you can see there, I have them here. And this basically what means that you have different type of photos. Some of them are colored, others are grayscale. The ones that are grayscale or black and white, of course, they have pixels, the one that I've showed you. And these pixels are basically dots in a photo. And if I make it 6 by 6, I'll have like 6 dots on the height and 6 dots on the width. And every single dot will represent the intensity of darkness or brightness in that particular dot in the image. And this usually range from 0 to 255. So I'll have a number that's ranging from 0 to 255 depending on the intensity of darkness or lightness in that particular place in the image. So if a place is white, you'll see more of 255. If a place is going to dark, you'll see a number that's close to 0. You'll see a number like 40, 30, 20 in that range. And you can see here, for example, 255 for the numbers that are like white, and then the ones that are close to black are going to like 40, a number close to 0. And so ideally, if you check on that, you can clearly see that you can convert images into numbers. So let me go back to my slides and continue with my presentation. Okay. Stop sharing. Okay. Present, share screen. These are just numbers, and I can in fact move from a grayscale image, get the matrix of it, the number representation of the image that I have. And that matrix, I can also convert it into a table so that I can see clearly where white is 255. And that's just black and white color photos. But what about the colored images? Can I also be able to understand them? How can I represent the colored images the same way I've been able to represent the grayscale? We have a range of use cases for computer vision, including self-driving cars by companies like Waymo. And one of the challenges you may face is that your car needs to quickly determine what is happening around it. It needs to see the environment and see, okay, understand what's in the videos that they're having. Of course, this cars has a range of sensors, including sensors giving them different type of data, from image data to LiDAR to radar and even video data. So, for example, assume that you're trying to see like a signpost, or a stop sign, signpost, a stop sign, and your self-driving car need to be able to tell whether what it's seeing is a stop sign, or probably it's something called a yield sign. So you need to have some techniques that can help you to determine that can help the car determine that what it's seeing, is it a stop sign or is it a yield sign? And we're going to use some awesome techniques called convolutional neural networks that are very powerful for processing images. And these algorithms are currently the best algorithms that we have for automated processing of images. And some of the things that you can do with them is, for example, I could show the image. I'm going to show you this on the code, but let me just show you this at the moment. I can show you I can be able to load the image, let's say from Colab. I can use matplotlib and then import image into memory from file or from somewhere, then display it using imshow, then have it the same way you see it. Okay, I think let me just show you the code and what we have. Stop sharing, go here, then I'll go back here, then share my entire screen. I'll go there, and then share my entire screen. Okay, I believe you can see my screen now. Perfect. Okay, yeah. So you've seen that already. And to move down here. My laptop is slightly slow, but we'll be able to manage. We'll manage it. Okay, so section 2, what about colored images? But even before you go into colored images, one of the things I want you to understand is something called indexing, how you do indexing on rows and columns, of course, for matrices. So you can have a matrix like this, and then you may want to be able to print, let's say, number 6. And to print number 6, you need to find ways in which you use arrays and get the columns and the rows where it sits. Of course, the row number is the first index and the column number is the second index. And that way, you can be able to get a particular number in a matrix. And this is very important because we're going to be able to try to do indexing on the different color channels for our images. Okay, and this takes us back to what Philomena taught on the first week. But let me just continue with these other ones. So one of the things I want to do is to visualize the stop sign I showed you on my slide. And I'm going to use matplotlib to display the image. To get the image from the library. Of course, I specify the path here. Then I read it using matplotlib there. Then I display the image using imshow. There you can see it. Where is it? Yeah. You can see it. And then I also want to get some spatial information from the image, like the shape of the image. What is the shape of the image that I'm having? And you can see here, I have 343 by 515, and then I have 4 here of my image. And I've been wondering, okay, I expected an image to have 3 channels. How comes the photo I'm having is having 4 in it? Because I expect to have like a 343, 515, and 3. And the 3 channels for the R, the red, G, the green, and B, the blue. But don't worry, I'm going to show you why we're having 4 in this case. So, of course, I've done the same thing again with this code. You can see here the dimensions, the height, the width, then the color channels. I have the 4 of them, and that gives us the shape of the image we're having. And there's something called an alpha channel that we usually have on our image. And it's ideally being used in something called transparency information on images. So there's a way that you can load your image, and then on top of the RGB, you can also have an additional alpha channel. So what you're having as number 4 here is basically an additional alpha channel that we're having on it. And then from that point, I also want to probably use the indexing that we talked about here at the very first part to be able to access, or ideally examine the red, green, and blue data in a particular pixel in our image. So I have, of course, I already know the rows and columns that I'm having for this image. You know that I have the height is 343 pixels and width is 515 pixels. But I want to go to the red part of my photo somewhere here and grab the red color on my photo. So, of course, I'm going to use indexing of rows and columns to get it. For example, here I've defined a row index of 100 and a column index of 150. I believe that's where I could get the red color. And then, of course, I have the RGB on 0, 1, 2, 3, R for the first one, then 0, 1, 2. Then once I have them here, I can be able to access them. Then once I access them, I can now print them. And when I print them, this is the value that I get from it. You can see I have red of 0.7450, green of this, and blue of this, meaning that what I have at that particular point is a red color. at that particular point of my photo. Then also I could try to do the same with how do I put it, with the green part. Is it the green part? The blue part. Yes, the blue part in my photo. I can see here the blue part of my photo. So I have 250 on the row index, 350 on the column index, and I can use the same thing to be able to get a blue in my photo. All right, so let me go back to my slide so that we do more discussion. Okay. All right, so we've gone through that. And so ideally, you just seen that images, you can convert images, just a matrix of numbers, and these images usually have some data in it. And computers doesn't see images the same way human beings sees images. All it sees is an array of numbers, the same way the ones that I've showed you. And color images are stored in 3-dimensional arrays. You have the red, you have the green, RG, then the blue, the RGB for it. And you can be able to find ways to access it, the way you can see on the screen. And you can also even go ahead and examine the red part, the green part, the blue part in a particular pixel of the image. You can do indexing into the spatial dimension of the image to get that information. Also, you could do the same for the blue one, the way I also showed you on the other side, where you could pick like an index. You can pick like a row and column somewhere and be able to check the color that you have in that area. You can even go ahead and modify the image where you can change the arrays in the data. For example, in this screen, what you can see on the screen here, you can set the green and blue values of pixel values to 0. And of course, the results of image will contain what you can see on the screen. You can even change the image, add some new thing on top of it. You could set the pixels within some part of the image to have no red color, no blue color, just the green with what you can see on the screen. So clearly you can see that images are just numbers, and I could convert my 1280 by 1280 image into, I can scale it into a 6x6 pixel image or 6x6 pixel image. And then from that pixel image, I can be able to have a matrix of numbers from it, 6x6 matrix of numbers, which I can also be able to have in a table, the same way I've shown you the table. Of course, the first photo is the original photo, but what you're having on the matrix and the table part is the resized photo, because I don't want to have the 1280 by 1280 rows and columns on my PowerPoint. And then once you've done that, of course, you can also be able to do something called filtering on top of this image. You guys use Snapchat and you guys use Instagram and all that, and I know you guys have been using filter, which in deep learning or machine learning, let's say in deep learning, you can be able to call them a kernel, where you can have a kernel that can run on top of an image with some steps on it and do something that we call an element-wise multiplication on top of it. Ideally, multiplying, let's say 1 by 255, 2 by 255, 1 by 255, 2 by 256, etc., etc., and then add all of them to get 2071. And by doing so, it can be able to extract features from 239. But maybe before I go deep into this, let me show you in the code how you can run different kind of filters on an image and the resulting thing that you can get when you run those filters on top of an image. Okay. So go here. Share the screen. Okay, entire screen. I hope you can see my screen. Then now I'll try to move to the top. So there's some amazing filters here that I've been trying to use to work on my image. Okay, my computer is slightly slow, but we'll manage. Okay. So I have a filter here. I have a range of filter here, and one of them is something called a Laplacian filter. And a Laplacian filter ideally help you to enhance the edges in a photo. And this is how it looks like, this way. And what I'm going to do is that I'm going to take the matrix in my photo, or rather I'm going to take this filter and then center it somewhere on the matrix in my photo, especially where I want to change or where I want to identify something unique. And in this case, where I want to identify the unique edges in my photo. And then I'm going to do an element-wise multiplication with this filter matrix, and also on top of my image matrix. And when I do that, this is what I get, something like this. But I need to show you it on an actual photo, how it will look like. So this is the original photo. This one is 1280 by 1280. This one is a grayscale. This is the resized photo, the 6 by 6 pixel. This is 1280 by 1280. But if I apply the Laplacian filter on that 6 by 6 resized photo, this is what I get. But to be able to show you how it changes on the photo, let me apply the Laplacian filter on top of my original 1280 by 1280 image. So I have a range of filters here. One is called a Gaussian blur, another one called Pewitt edge detection, another one called, of course, I've talked about Laplacian filter. We also have Sobel edge detection and a range of them. And I can upload my image and then run it on top of it. You can see here, this one removes everything and just enhances the edge detection part of it. This one here blurs my images. You can see the Sobel one. I can also brighten the image and ideally do a range of things with it. I can do the same with Keras as well. And at the end of it, have a resized photo. I don't know why it hasn't come here, but I can rescale it. You can see here, I can set a crop it. Of course, with that, I can also do things called augmentation. And by augmentation, I basically mean I can rotate it, flip it into different angles on my photo. Yeah. So let me go back to my slides. Share window here. Okay, yeah. And the most important thing you can pick from that point is that all these different filters, when you run it on top of the image, they're going to identify a unique thing in the image you're having. For example, you've seen that the Laplacian filter, if you run it on top of the image, it's going to identify the unique edges in that photo. And the process of doing an element-wise multiplication between an input image with a filter is something that we're calling convolution. So ideally, we're having something called a convolution, and a convolution layer, what it does is that it applies a kernel or a filter over the regions of an input image, the same way that you've seen it, the same way it's moving on it. And if you do the same, this is what you've seen it, and the entire thing at the end of it is going to help you to extract features. So unlike machine learning, where you do feature engineering, here you could use convolutions and filters to run on top of your image and extract for you the features from that image, unique features from the image. And when you're just starting, it's going to extract like few things like edges on the photo. But as you have more and more filters, you're going to be able to extract features that could give you the shapes, objects in that photo. And the more you add more and more filters, you're going to reach a point where instead of just detecting the edges and shapes, you're going to detect things like the nose, the ears, the eyes from that particular photo. And of course, you're going to have more and more and more of filters and more and more and more of photos. And therefore, you need to find ways in which you reduce the dimensionality of what you're having. You're going to need to do something called max pooling that helps us to reduce the size of the image by summarizing the regions of this particular image. And it's going to reduce the size, but not just reduce the size on its own, but also enhance the features in this image. It's going to ensure that when you're building your model, the way Philomena talked about our model, it's going to pick the most important features in that photo and propel them or propagate them to the next features, to the next layers in your model. So the things that doesn't really matter, it will leave them. But the things that really matters, it's going to pick them, enhance them, and then propagate them to the next layers in your model. and that entire thing is called max pooling. So if you do max pooling and if you do convolution and you do max pooling, and there's something else I'm going to talk about called activation functions, or adding non-linearity to your data, because the data that you're having is not usually linear. You can't map that data with, let's say, a linear equation. You have a range of distributions that you can't map with a linear equation. So you need to add some non-linearity to it so that your function or the kind of model you're going to build is able to map this complex distribution. So once you've done convolution, done nonlinearity, and then you, of course, Philomena has talked about activation functions such as relu, the celu, the stanch, a range of them. So once you've done all that, then you do max pooling to it. You'll be able to have a data that now you can use to do a range of tasks with it. But this first part of it that I'll be taking you through is just something called data representation. How can I represent my structured data, or how can I represent my unstructured data before I use it for a range of tasks for computer vision? And then now we have values of X. And machine learning is ideally, or deep learning is ideally trying to get the best equation, or trying to get the best distribution that fits our data that we're having. So we're going to have data, the one I've shown you, that fits our X value, the pixels or the matrices that we have, that we've already added a convolution to it. We've already done a max pooling to it already. We've added an activation function to it. And now we have the X part of our data. Let me just grab a pen so that we can get the point. So we have the X here, and that X basically represents what we've collected already as our feature. And we can say that now what we're having at that point is our feature map. But this equation still has a range of things on it, which I'm going to break down into pieces so that we're able to understand. But I want you to take machine learning or deep learning to be just you try to approximate Y as a function of X. But of course, you also have a range of things here like W, you have the sigma here, you have B as well, which I'm going to break down and talk to them about. So the first one is going to be this activation function. And I'm glad that Philomena was able to list them with their names, like relu, celu, tanch, a range of them. But ideally what it does is that it's going to enable us to map complex data. Of course, I've also talked about the same as well, but it allows us to be able to map complex data in the entire idea of trying to approximate Y as a function of X. And that's what we're calling an activation function. And there are a range of them. Yeah, for example, here you can see we have one called softmax. I've talked about X already. I've talked about weights. Weights, you could take the filters as your weights. Of course, sometimes you initialize them randomly, but you could take the filters matrix as your weights. And X, you could take the matrix from your images as your X value. And then I've talked about nonlinearity. Let me not go back into it. And that entire thing is something that you're calling a convolution neural network, where you have an input image. That input image, you apply something called a convolution to it. And that convolution, you also apply something called an nonlinearity to it. And at the end of that, you'll be able to have something called a feature map. And that feature map, you can be able to have something called a feature map. Of course, before you have the feature map, and once you have that feature map, you can be able to now to add it to something called a fully connected layer. But I'll go into that later. So input image, convolution, that involves the filters, the image information, the activation functions, then the max pooling. And from that point, you could say that convolution neural networks involve the three steps. One is convolution, where you're applying a filter to generate feature maps. Second one is a nonlinearity, where you use a range of them. Sometimes you can use ReLU. I've shown you the other ones. Then you do pooling to downsample the operations of each feature map. And you can see here how you can also apply the same with Keras. You can see conv2D here to do convolution for 2D data. You can see the activation function here. Then you can see the max pooling for 2D as well. And then that means you're done with the first part for feature engineering or feature learning, which you have here. Then we also have a second part for tasks. So it depends on the task that you want to do. And you could say that also, when you do this entire thing, these convolutional neural networks, or something we call convnets, they're used for image classification, and they usually consist of two main parts. One is a convolution base, and the other one is a dense head. And that then the other one is a dense head. And the base is used to extract features, of course, from the image, and the head is used to determine the class of the image. And then probably also wondering, what exactly do you mean by visual features? And these visual features, they could be the line, the color, the edges, the shapes, the texture. And ideally, these features actually, what you're seeing here is like a basic thing, but that entire thing is the idea of how you could extract features from an image. Then once you have those features, you can now go ahead and do classification, you can do object detection, you can do segmentation, you can do probabilistic control, you can do a range of computer vision tasks, because now you're ready with your features, and what's remaining is just doing the tasks with them. But there's something we haven't talked about, which is the why. What about this why? Yeah, of course, in the first lesson, we say that why is the target. It's what we want to predict. But imagine, for example, that you have you want to do image classification, and you have images of three classes. You have a dress, you have a t-shirt, and you have some shoes, and you'd like to build an algorithm that can distinguish between these classes. Of course, this one is called a classification task, and we have the training phase, and in that training phase, we present an algorithm with samples from three classes. So you have a shoe, you have a t-shirt, and you have a dress. And at the end of the training, we would like to know how well our classifier is working. And then, of course, we're going to have them like this. You have like shoe, dress, shoe, t-shirt, like that. And we're going to find ways in which to classify all these ones, and then see how well our equation or the distribution that we mapped is working. But how do we represent that data? How do we represent the data for classification? So to do that, we'll go back to what we learned in our second week, and that's basically how to handle categorical data. So I hope you guys really remember what we talked about on week 2, where we can use maths to represent the data in something that we're calling one-hot encoding, where in the original data set, we can have a color as a categorical variable with 3 categories, where we have the red, we have the yellow, and we have the green. And then the corresponding one-hot encoding can contain 1 column for each possible value and 1 row for each row in the original data set. So you can see here, you can have like red, and then you have like a row, and you only have 1 where red appears. But if red appears, you'll have 1 on the red. If red doesn't appear, you'll have 0. If green doesn't appear, you'll have 0. But if yellow appears, you'll have 1 at that particular point. So ideally, that's how you could represent our categorical data. In this case, where you have the shoe, dress, and the shoe and dress and t-shirts, and ensure that you have it this way. And where a shoe appears, you'll have shoe on that particular column. Where dress appears, you'll have dress in that particular column. And this entire thing is called one-hot encoding. And that's how you can be able to have like your Y values. And then once you have your Y values, you're going to now do your deep learning, or you're going to find the equation or the best equation that represents the distribution or that fits the data. Or you're going to find the best distribution that represents the data that you're having, or the data that you're having. And then once you have that, you're going to make a prediction. But of course, when you make the prediction, most of the time it's not going to be accurate. So you're going to find the ground truth, the true values, and the predictions that you make. And your goal is going to ensure that the predictions that the equation you're going to build, or the distribution you're going to map, is going to be as close as possible to the ground truth. And when you make the first prediction, of course, most of the time it won't be correct, and you're going to find ways to get the difference between the ground truth and the predicted value. So you're going to subtract the predicted value from the ground truth. And once you do that, you can do the calculations of the error, then plot it. The different ways to calculate these errors, one of them include mean absolute error. There are also a range of others, but you can get the error from what you've done, from the prediction you've done. And once you've done the error, your goal is going to ensure that you reduce that particular error that you've got. So to reduce this error, the range of techniques that you can use, including plotting a curve called a loss function. And that curve, you, of course, on the y-axis you have the loss, and the x-axis you have the weights, and your goal is going to be to find the best weight, that gives you the least weight, the least loss on the y-axis. Get the best weight on the x-axis that gives you the least weight, the least loss on the y-axis. And then you're going to iterate the same over and over again over a series of steps until your loss is almost close to zero, or until your equation almost maps the ground truth equation. Of course, what I've taken you through is something called gradient descent, where you descend down that loss against weight curve, and you're going to move down to a point where at the end of it you find like the best equation that maps what you're having. And then once you've done that, you also need to find ways to have like the best equation from it by ensuring that the equation you have doesn't do something called overfitting. It doesn't just map a particular kind of data. For example, if you're having, let's say, shoes, it doesn't just map red shoes, but ignores a blue shoe when you make it, or a black shoe when you give it a black shoe to do inferencing on it. So you need to ensure that, number one, the distribution that you're mapping, or the equation you're building, or the model you're trying to build, it's going to classify for you images. It's not going to give you wrong predictions. And by not giving you wrong predictions, I mean, it's not going to be poor at predicting the things you're giving it. And you need to ensure that the equation you're building is just right, in the sense that it's not overfitting or underfitting. I've talked about that already. Of course, you can do things. You can plot training laws and validation laws as a function. You can plot both training laws and validation laws as a function of the number of iterations, which is epochs. Philomena already talked about epochs, so I want to go into it. But a generalization curve can help us. It can help you or help me detect the possibility of overfitting. And of course, the different ways in which you need to go down the curve, they're called learning rates. Sometimes if you choose like a too small learning rate, the gradient descent may be slow. The entire process of training will be slow. And if you choose like a large learning rate, then you're going to overshoot to a point where you can't reach the global minima, or the global place where the best weights give you the least loss. And there's also something called batch. You can think of batches as the different rows, or the number of rows you'd want to use when in each step of the training. So how many rows will you want to use? Will you want to use 20 of them, or 30, or 40, or 200? How many rows will you want to use in every step of the training? So that's the batch. That's the batch usually defined in your function. Then there are also other different ways to reduce overfitting, including dropout, batch normalization. Of course, Philomena talked about this. Let me not go into it. But at the end of it, you need to find ways in which you can be able to get the equation that is not overfitting or underfitting, but is just right for what you're building. And I know at this point, probably you're wondering what you're showing us. I mean, this is the same thing we're seeing in machine learning. How is all this different from deep learning? And all this, you could say, machine learning most of the time deals with structural data, and deep learning most of the time deals with unstructured data. Structural data includes things that are in an Excel sheet that has rows and columns. And unstructured data include things like images, audio, video. Those things include the unstructured data. And for unstructured data, and in deep learning, you're going to use neural networks to learn the features automatically from it. So those are some of the key differences we have for classical machine learning and deep learning. And of course, Philomena talked about the difference between artificial intelligence, machine learning, and deep learning, and I want to go into this. But I want you to understand the key ingredients for deep learning that include a data set. How do you get your data set? How do you represent that data? There's a model and layer. And by the way, a model is just a container of layers. I know probably wondering, okay, you have model and layers. What's the difference between these two? So a model is ideally a container of a bunch of other layers. For example, in Keras, you can have something called sequential model. And that sequential model, you can have a model where sequential model, and inside it you have layers like dense layers, activation function, etc., etc. So you could think of let's say a sequential model as a foundation. Then all these layers are laid on top of each other if it's sequential model. I've talked about the cost and optimization, and you realize that all this involve a lot of mathematics, all this involve a lot of computation, all this involve a lot of matrix manipulation. They involve a lot of variables and parameters, and sometimes you can, and it will be very hard for you, even if you're good with mathematics, to sit down with your book and a pen to calculate all the gradients for them, and do all the linear algebra for them, and do all the probabilities for them. And therefore, you need a tool that helps you to do things called automatic differentiation. But even before you have the automatic differentiation, you need a tool that can help you define the layers, help you define the model, help you define what you're trying to build, so that at the end of it, you can give it to an automatic differentiator to do for you the mathematics. And this is what we're calling Keras. This is where Keras comes in, and Keras ideally help you to accelerate your machine learning building process. And the funny thing is, the mission statement of Keras is to give you, or to give an unfair advantage to any developer looking to ship machine learning powered applications. And the idea is that you don't need to create your entire machine learning architecture from scratch. You will have some reusable, small, cool elements that you can use inside of Keras. So you don't necessarily have to go and build things on your own from scratch. You have things that you can reuse that can help you to define the layers, help you define activation functions, help you to compile your model, help you to check on the metrics, check on the loss, and all that. But ideally, the way Philomena put it, Keras provides a high-level APIs for building deep learning models. And then the other automatic differentiators can be able now to do for you the automatic differentiation. But you can also think about Keras as what you see on my back here. You can think about Keras as blocks. So you can imagine your entire machine learning model as a house that you're trying to build, or as a castle, or as a Lego block that you're trying to build. And Keras, what it gives you is the building blocks, consistent building blocks, and simple APIs that you can use to build your house. For example, if you need a door to get into the house you're trying to build, then Keras will give you something called a data loader. And it can also give you a range of other things that you can use to build this house that you're trying to build. Of course, Keras is developed by someone called Francois Cholet. But let me not go deep into this. Let me just talk about other things. And these blocks include the necessary imports. They include things like data pipeline. They include things like model construction. They include things like model compilation, model training, and inferencing. And please take note of this, because this is really important, especially when you're building machine learning models or deep learning models. These are the key steps that you take when you're trying to build your model. Of course, the first one is the one for importing the necessary packages. We need TensorFlow, we need Keras, but not what you're having here today is slightly different from what we're having in the latest release of Keras, which is the Keras core. So in Keras core, there's a new total way of doing this entire importing these packages that you need. You also have a pipeline or something called a data loader, and everything that comes through that ledger door, or that door that you're having, is going to be shuffled, is going to be rearranged, is going to be randomized to prevent the model from learning the order of data or individual unique features, and ideally improve generalization performance of the data. You remember we talked about generalization on the previous slides. And then they're going to be neatly packaged into groups. And this entire thing is called batching, the batches that you normally see in your data. And we do batching because batching improves the efficiency of training this particular model. And then you're going to do specific operations. You're going to apply some specific operations like map to them and a range of things. But that's just the data pipeline. Then you also have the sequential layer. And in Keras, every neural model is an instance of a sequential object. And you could think of a sequential object as a container for your network. But if you go to this analogy that I gave you, you could think of a sequential layer as, or a sequential object or model, you could think of it as a foundation for your block. It's a foundation where you're going to lay the different dense layers on top of it. So you could think of sequential object as a foundation, and you could add layers as to the sequential object on top of each other, the same way you'd add blocks to the foundation of a building or a house. And then you'll have layers on top of it, and these layers, they could be the dense, this you could have bricks on top of the foundation, and these bricks are the dense layers that you're having on them. And of course, you also have activation function in the entire mix. And in the analogy, you could think of an activation function as the mortar that's between the different bricks, the mortar or the glue that attaches that holds the blocks together. And of course, Philomena talked about what a dense layer is, which is basically a fully connected layer that connects every neuron in the previous layer to the neurons in the next layer. And finally, you compile your model or start assembling your ledger block into specific structure. You'll define the optimizer. We talked about optimization, or how you can reduce your loss when you have a curve of loss against weights, and how you could descend down, or how you could use different techniques to reduce that loss. One of them is something called an RMS prop or RMS propagation. I think prop is for propagation. But before you do the prop, of course, you need to do the loss. You could use different techniques like mean absolute error on it. But ideally, the optimization helps us to get the best set of weights of the neural network that give us the least loss. And loss is ideally the measure of how well our model is performing. Then you do the model training the same way you do the fitting. That's how you do the fitting here. You have epochs. Philomena talked about epochs. Then you can do model inferencing. And yeah, that's basically how Keras fit into the entire deep learning thing and fit into the entire computer vision thing. But let's see how to build a model with Keras. There are different ways in which you can build a model with Keras. Of course, we talked about the sequential model, and the sequential model is usually the most approachable API, and it's basically a Python list. It may be limited, or rather it's limited, but ideally what you're trying to do with it is to stack layers on top. You'll have it to create a container where you'll stack layers on top of each other. Then the other one is something called functional API, which focuses on graph-like model architecture, and it gives you the midpoint between usability and flexibility, in the sense that you can define your inputs, define your outputs, and even put them together. So you can use them in different ways. If you are just a novice user or you want to work on simple models, you can use sequential API plus built-in layers. If you are an engineer with a standard use case, you can try to use a functional API with built-in layers. But if you're an engineer who want to work on a niche use case, then you may try to use functional API with custom layers. There are also other things called subclassing, but I think we'll organize like an entire session to dive deep into Keras and talk about sequential API, functional API, and even model subclassing or layer subclassing. This is how a sequential model looks like. Philomena has talked about this, but I won't go deep into it. Maybe I could just mention that 64 represents the number of neurons that you're having. Then you have the activation function there, the ReLU. You can also have a dense layer with, let's say, 10 output from it. This is one way of doing it. This is another way of doing it. We just add the models to the sequential layer. But Philomena has talked about all this, so I won't really go deep into them. You can also do like a summary of them and see them. There's also functional API. Of course, sequential model is easy to use, but sometimes its applicability is limited, and therefore you may want to go and use the functional API. so that you can have multiple inputs, multiple outputs, or multiple inputs, a single output, and a range of them. Okay, so ideally this is how a neural network is structured. You could see the first layer, you have like 32 filters, you have filter size, you have the activation function. Filter size is a 3 by 3 matrix, I think. Then you have like a max pool, you have a grid of pool size 2 by 2, then you have a stride of 2. Then there are 2 convolution layers, then you have a dense layer or a connected classifier, what we've talked about already. I could show you some code, but I think Philomena has talked about this, so let me not go into it. But on top of this, I just want to add that now we have something called Keras CV. Since we're talking about computer vision, I should also give you like some cool things that Keras today has, like Keras CV, that you can use for things like image augmentation, ideally just flipping the images, rotating them, and the range of them from aug mix to cut mix to Fourier mix. Sometimes if you're confused on the one to use, you can use the rand mix. Then you also have Keras CV for object detection. You can do image segmentation, like what you can see on the screen. I've seen a lot of this on self-driving cars. You also have the hottest thing today for generative AI. You have something called image generation, and you can use it supports pre-trained stable diffusion model, both version 1 and version 2. You can even extend textual inversion and do things with the dream booth. Yeah, and I don't know, after that point, I don't know if you guys have questions. But I think I'll answer them since I can't see them. Let me just finish with this one thing or quote from Francois Cholet. That the whole idea of Keras when you're trying to build your deep learning model is that simple things should be simple. But even a simple thing as simple, still you should be able to do complex things with it. So I want to go deep into this. I think let me just end it there. And thank you very much for listening to me. I'll pick the question after this session. So from this point, I want now to hand it over to Brian. Brian, can you hear me?
Yes, I can hear you. Can you hear me?
Loud and clear, Brian.
1 minute. Okay, so I have my slides. Maybe you can share them for me.
Okay. Yes, there they are.
Okay. So hi everyone. Thank you so much for joining the call. I know you've had a lot of amazing things, a lot of things to do with Keras, things to do with TensorFlow, things to do with the, amazing Keras spirit that you have. So I'm going to talk about structured query language, which is something we should not put it down, or we should not, tusipuzie sana, tuitilie manani. It's something we should also consider as data scientists or machine learning engineers, because it has been in existence for the longest time, I guess, and tools like TensorFlow, Keras have come, but it is still also strong and people are still using it. So I'll be talking about the fundamentals of it and how, as a data scientist or machine learning engineer, you can step foot into it. I know it can be challenging, but as we always say, hope you see the glass as a glass that is half full, not as half empty. View the fullness perspective and not the emptiness perspective. And I'm sure this session will be amazing. So in this session, I'll try to be, since it's already 9:18 p.m., I'll try to be as precise as possible, but still try to explain things to you in a way that all of you leave this session understanding how you can use structured query language in building machine learning models. So the role of databases and SQL in the tech landscape. So that is what I'll cover. Then we'll understand relational databases, and then we'll also try and see how one can query and transform data with structured query language. So the first thing is, why should we learn structured query language? Even in this study jam, we were supposed to only cover the deep learning part and the computer vision part, but we saw it fit to bring it to you that you should take structured query language as something that you can put on and you can learn. So business and technology professionals can both reap the benefits from learning structured query language. SQL is a highly lucrative skill to have according to the Stack Overflow annual survey. This is not me. There's an annual survey by Stack Overflow, and it's still a lucrative skill to have. It can be utilized and open up many career paths in both business and IT, both in analytics. When you know SQL, you can work at analytics. You can still work in ML. You can still work with cloud platforms because now we have tools like BigQuery ML, which use from Google Cloud that use SQL. So in the business side, you can do analytical, managerial, strategic, research, and project roles. In the technology side of it, you can do database designing, database administration, system engineering, IT project management, and software development. I'm sure most of us already understand structured query language. So yeah. So let me now introduce the concept of databases. So a database a database is anything that collects and organizes data. So for example, if I'm washing dishes and once I clean the dishes, I rinse them, the fact that I have a rack that where I wash the plate, I organize this plate at a specific place. When I clean the spoon, I put the spoon at a specific place. So I'm calling the rack a database because it's something that can collect and organize my plates, my spoons, my knives, like my utensils in the house. So view databases as anything that can collect and organize data. And in the first session, I said that machine learning has become more and more accessible to people because you have amazing tools like TensorFlow and Keras, and SQL is one of them. So, and data is the heart of models. Data is the heart of machine learning models, the heart of AI, and it's the one that determines how good or bad something is. So examples of these are Excel spreadsheets. I'm sure we all have worked with Excel once, at least once, either when you're being checked in at tech events. I'm sure in most tech events, when at the registration desk you meet people with Excel sheets and they're there, hey, did you register? What's your name? So Excel spreadsheet is one of type of a database. Then you have text files like comma separated values, that is CSVs, XMLs, JSON. We also have a file cabinet with organized documents. So those are just simple examples of what a database are. But when referred to professionally, a database is typically a relational database management system, that is an RDBMS. So relational database management system is simply a type of database holding tables that may have relationships. So we understand that in this world, we can't exist without having relationship, either if it's work relationship, personal relationships, family relationship, but we need relationship. Now let's view relational databases in the same perspective. We need relationship and we can relate to one another in a very family relationship have their own importance and friend relationship have their own importance. So a field in a table can point to another table for information. So let's view this table here. It has a customer order. We have the customer order table and the customer table. So in the customer order table, we have the order ID, the order date, the shipping date, the customer ID, the product ID, the order quantity, and if it was shipped or not. So for most of us who receive, for all of us who receive swags, this is something, maybe let's see if this is swags being shipped for Keras Community Days coming to Kenya. So we have this is our customer order, and then you have the customer name. So the customer ID. So you see, we have the customer ID is linking the two tables. So in real life relationship, this is how maybe you can view the idea of having two tables. So what is linking a relationship between me and my brother is because we are brothers, we are from the same mother. So we share maybe a son. Let's say we share the name Kai or we share the name Wanyumba. So that name is linking the two of us. And the thing that is linking me and Marvin Gesser is that we all do machine learning and we are very huge fan of the Keras spirit. So Keras spirit is the primary key between me and Gesser. So it is linking the two of us. Let's go deeper into this. So why should we have separate tables? We can have all this in one table, like your Gen Z, no wahala. We need to have all this done and dusted. So this idea of separating different types of data, e.g., the customer versus the customer order, is known as normalization. So it's a concept called normalization. Putting both customer and customer order information in one table will be bloated, redundant, and difficult to maintain. So normalization helps us to achieve non-redundancy. It helps us to achieve it helps not to bloat our data, and it helps to make our data easy to maintain. So when we do that, we can now easily maintain our data, and our data is not bloated. So I have an example here where, let's say, one person has ordered several items. So let's say Marvin Gesser, Marvin Gesser, and Marvin Gesser. And Marvin Gesser has ordered hoodies for Keras Community Days coming up. So you see, like, imagine if you needed to change an address. So let's say Marvin Gesser is no longer in Nairobi, but has decided to come and take maybe some relaxation in Kisumu before coming for some staycation in Kisumu before coming for the Keras Community Day. So they want to change the address where they'll receive the package. So now imagine if we need to do this, we need to change an address and we need to do it 3 times. Like we need to come here, change this, changes, which will be so tiresome. And now you can imagine, it's not, this is just an example. You don't have Marvin Gates alone ordering. I'm also ordering, let's say I love aprons, so I'll order aprons. Let's say when Gaku is ordering for us Bluetooth speakers, so they also have Bluetooth speakers there. DC Okache is ordering for us, let's say Vitenge, and you have Vitenge there. So you see all those, and it's different customers. So it can be very hard for us to change stuff. So let me now ask, I know maybe I can't interact with you directly as my audience, but maybe you can drop one in the chat section, on the YouTube chat section, if you feel like this table is normalized, and you can drop 2 in the chat section if you feel this table is not normalized. So I'll give like 20 seconds and proceed. I understand we have a challenge where maybe it's hard for me to know if you have dropped the answer or not. But yeah, let me now explain if this table is not normalized or not, because these are the literal basics of understanding the relational databases. So this table is not normalized because you can see you have Jonathan Reyes, and Jonathan Reyes here, and the birth date, you can see the birth date is the same. So we're like repeating stuff in this table. We also have Rebecca. We're like repeating Rebecca in this table. So we don't want that. So what you can do is you can have, so in this table, it's an appointment, let's say sheet. We have an appointment ID, the patient's first name, the last name, the birth date, the visit date, the check-in, and the checkout. So we can decide to have these 2 tables. We have where one is a patient table and the other one is an appointment table, where the patient ID links the 2 together. Yeah, so you can see the patient ID is linking the 2 tables together. Thank you very much for joining us from Bungoma. We are so happy to have you here. So you can see in this table, we have 2 tables, the patient and the appointment table. In here now, at least these tables are normalized because you're not repeating information. And the information here can be linked to the information in the appointment table by having the patient ID in both tables. So you can see in our previous table, this is what you can see. And in this table, in these 2 tables, this is what you can see. So at least it is normalized and easy for someone to like query information. So now I hope you've understood that concept. Now let's understand what are the different types of databases. So relational databases and SQL are not proprietary to one company or organization. Many companies and organizations have created their own relational database software. So we have MySQL, Microsoft Access. I'm sure if you did computer in high school, you came across Microsoft Access or something. You have SQLite, Oracle, Microsoft SQL Server, PostgreSQL. All these are different types of database software. But please do not be confused by SQL being used to brand database software like Microsoft SQL or MySQL. It is the universal language used in RDBMS platforms. So it's like the universal thing linking all these database platforms, software platforms together. So let's go to the next slide. So now there's this issue of having no SQL, no SQL, no SQL, however you decide to pronounce it, and big data. So we have understood what relational databases are, they use SQL. So now we want to understand what are NoSQL and how are these NoSQL relating to big data, because this is AI and amazing things that we've seen Gesa do with filters and all that and images. So NoSQL stands for not only SQL, and it's often used to describe big data platforms that may leverage SQL but are not relational. So they are not relational in those terms, but they may leverage SQL. So no SQL databases include MongoDB, Couchbase, Apache Cassandra, or Redis. So if you deal maybe with analytics of big data and big data stuff, you probably had these words, MongoDB. I'm sure the MongoDB community in Kenya is very active, and I'm sure you might have joined one of the events. So these platforms store massive amounts of data in a variety of raw and structured formats. So Ngesa shared the difference between, if I also shared in the first session where I talked about decision trees and all that, the difference between structured and unstructured data. So in NoSQL platforms, they store massive amounts of data in a variety of raw and structured formats, i.e. we can have documents or key value pairs. So most of these solutions are distributed across multiple machines, which is difficult to do with relational databases. In machine learning, we have a concept of distributed learning or training. With distributed learning or training is where instead of training everything on a machine, I have different machines, and I let this person do this person do this, and this person do this. And at the end, I have an amazing thing. So now let me give you an example. So let's say we're organizing Defest Lagos. And in Defest Lagos, you have people who have different passions in community. So one person decides to work on, let's say, coming up with a website. The other person decides to come up with dealing with sponsors. Another person comes up with deals with speakers and all that. So you see, we are distributing our organizing into different parts, and with this, we're able to maximize on our outputs while also reducing on the time one person would spend in doing all the tasks alone. So that is what distributed means when even it comes to big NoSQL. So other big data solutions such as Apache Hadoop and Apache Spark can be interacted with using SQL, but are not limited to relational databases. So you can still do relational databases stuff in this platform, but they're not limited. You can do much more amazing things on these platforms. So caution, using NoSQL and big data. So this is just a question using NoSQL and big data. When all you have is a hammer, everything starts to look like a nail. So when you are in high school, everything revolved around you having specific things or you doing specific stuff. That's what it means when all you have is a hammer, everything starts to look like a nail. So don't fall in the trap of treating all data problems as big data problems, because most are not. So, like I said, not all problems are supposed to be solved with machine learning to start with. Not everything you come across your workplace can be solved with machine learning. You have a lot to consider: ethical considerations, explainability, AI. If you cannot explain a product, then that's not it. If your product is not ethically right, then that's not it. So let me give an example here. So for example, Twitter had an automatic which was trying to resize your image. So when you post an image on Twitter, it used to focus the image. But this feature became biased in that it focused greatly on whites and didn't focus on blacks, and the feature was scrapped. So you see, AI was not a solution in that case. So don't fall in the trap of treating all data problems as big data problems, because most are not. So we also have the silver bullet syndrome, but I've attached a link. I will not go deep into that. Maybe you can go deep into that after the session. Oops, sorry. Uh-huh. So now let's understand the different what we mean by SQL and NoSQL, and where do we use which? Which is which? We've learned about a lot of things: deep learning, Keras. Now we're talking about SQL. So I want to make this as fun and engaging as possible for you to understand these concepts at the back of your mind. So what is the difference between SQL and NoSQL? So we know when you're building machine learning models, we go for specific things. So I can use, let's say, a tool or a technique because my problem is best suited for that, or that technique helps much more with my problem compared to another technique. So let's understand. The first feature is integrity or consistency. So with SQL, data is enforced with logical relationship. Like if university course is equals to microbiology, then do this. So you see, and minimize redundancy. So you have minimized redundancy and up-to-date consistency. Up-to-date in quotes. But in NoSQL, simple key value and document storage does not enforce any rules or structure. Redundancy and write latency is common. So when you want to deal with integrity and consistency, the go-to thing should be SQL. That's why I write the winner here is SQL. But that doesn't mean that NoSQL is not good. It's good, but you just have to weigh your choices well. And then you have design changes. With SQL, it is easy to add to database, but hard to modify. It is very easy for you to add something, but hard for you to modify. No SQL, you can quickly and arbitrarily change what data it stores. So if you are going more for design changes, then the winner here is no SQL, and you should maybe probably pick a no SQL solution. And then let's look at analysis. So SQL is a universal language that makes accessing and analyzing data simple. So it makes accessing and analyzing data very simple for you. But SQL support is sparse in NoSQL tools, and proprietary languages are esoteric and hardly universal. So if you want to go for analysis more, then you can decide to go for SQL. So SQL is the winner here. Now let's look at the other feature, which is programming. So programmers of Java, Python, .NET have to map entities to tables, which can be tedious, but data integrity is given. And with no SQL, programming against a no SQL database is quick, simple, but honest is one programmer to validate data. So you see, if you decide to go with your feature is programming, then you have to draw and actually see maybe what works best for you here and what does not work best for you. Because there is no like better one here. It's you to decide on what you're building and what stuff you're trying to achieve. And then you have performance. So relational databases can store data for most use cases, but struggle with true big data cases. Integrity constraints also slow down performance. So it can store data for most use cases, like for simple use cases. For example, let me pick a use case. Okay, this is a good use case. So for example, I come from GDG Pwani. Of course, I'm part of GDG Pwani, and as GDG Pwani team, we are planning to build a project to help fish farmers throw less waste to the sea by having award points for them. So we develop these trackers and attach them to their boats. And so this is like an IoT camera that is attached to their boat. So the less waste they drop, the more points they have. So you see, that makes them throw less waste to the sea. So if that is my use case, then I can just say these relational databases may not work because I have big data. I have to take videos, we may have to take pictures from the boat and all that, which might be hard for me to achieve. But with NoSQL, it is capable to store vast amounts of data with horizontal scaling. It also performs quickly due to horizontal scaling and no integrity constraints. So you can see if I want to use maybe cameras and all that stuff to do amazing things with GDG Point and help the coastal community and reduce wastage, then it will be very easy for me to use NoSQL product. So here the winner is NoSQL. So now I hope you've understood the difference between SQL and NoSQL from a feature perspective, like from how you want to solve stuff. Okay, so I see my slides are back up. Let's go to the next feature. So just to mention is that SQL is integrity and accuracy. NoSQL is speed and scalability. And SQL should be a prerequisite before learning NoSQL and big data. Like this is very important. It will be very easy, not like it's a must, all of us follow different paths, but it will be very easy for you to pop into Apache Cassandra and all that if you already have an SQL basics. to build upon it and do that stuff. So yeah, if you're absolutely uncertain which to use, then start with SQL. Go with it in your ML problem farming. I talked about ML problem farming in my last case, or in whatever the problem you're trying to solve. And then try and see when you meet an obstacle that now requires no SQL, then move to no SQL, which should be easy. But if you're certain that you need no SQL, then start with no SQL. If you're not certain, then you can start with SQL. So now let me talk about lightweight versus decentralized databases. Because I understand, even though we want to build amazing stuff, maybe sometimes we are limited. We just want to build small fun projects. Or let me say, I'm just a part of Google Developer Student Club's tool, and I just want to build a project to help me detect the number of maybe inclusion and diversity in my community by checking the number of attendees who come into my event. So you see that is a small project, but maybe I'm part of DDG Pwani, and I want to build the project I shared earlier on helping fishermen from the coastal region dump less waste to the ocean or no waste at all. So now let's understand what lightweight versus centralized databases are. So lightweight databases these are used in this specific use case when you want a simple solution for a small number of users. Lightweight databases are a great place to start. So I'm just a Google Developer Student Club at Technical University of Mombasa. I want to measure and record the number. I want to measure and record and give value to my efforts in ensuring diversity and inclusion for my diversity report at the end of each quarter. So I just decided to use lighter databases to store the contact, maybe the information of the different students that come into my session. So the data is stored in files and can be shared, but can break when edited simultaneously. We have seen this when many people are coming to the event, and now people at the registration desk have to edit the files simultaneously. It just causes chaos around that place. So maybe you can also build a solution around that. I've mentioned this many times. The check-in process at events. How have you seen it? This is just out of the topic, but how have you seen it? Do you want to see it more streamlined and all that? You can build a solution with AI and SQL. Who knows? So common lightweight databases include Microsoft Access, SQLite, and H2. If you did computer in high school, I didn't do computer in high school personally, but I know my friends who did computer did this Microsoft Access wahala here. It's not wahala, but Microsoft Access stuff. So now let's understand centralized databases. So when you need to support tens, hundreds, or thousands of users, so when GDG Pwani are building this, GDG Pwani are not only looking for people in Mombasa. We have the ocean in Mombasa, we have the Kilifi Creek, we have the Malindi, we have Lamu, we have Lake Jipe in Tatataveta, we have Lake Chala in Tatataveta, we have all those lakes, and coastal Pwani is blessed. And if GDG Pwani decides to go with this, they'll be serving tens and hundreds of people with their product. So you see, they're looking at big products. So these databases are designed to handle a high volume of traffic efficiently. So imagine all fishermen usually fish at night. So imagine Lake Jipe fishermen are fishing, Lake Chala fishermen are fishing, maybe the South Coast fishermen are fishing, North Coast fishermen, Lamu, all those are fishing. And maybe decide to even partner with, let's say, GDG Zanzibar. So also people from Zanzibar, Dar es Salaam are all fishing, So we need to regulate traffic efficiently. So we need to handle traffic efficiently, and we'll receive a high volume of traffic. So some example of centralized database platforms include Oracle, Microsoft SQL Server, MySQL, PostgreSQL, and Teradata. So this all depends on also which platform, all the platforms are amazing. It just depends on what do you want to build and what you use case. So let me share with you a typical centralized database setup. So we have a client, an SQL user 1 and SQL user 2, and then a laptop with MySQL. So this is a type of centralized, which has maybe 2 users and uses a client server setup with my laptop as an SQL. But let's say these are tens users. Now I'm building to hundreds users. So for production, you typically use a server computer to host that database rather than a laptop or a desktop. So this is now going to production. With the first one, This is probably when I was building our MVP for GDG1. We just used 10 people and then used all this. But now when you're deploying it to maybe, let's say, fishermen that only come from Lake Jipe, Lake Chala, and North Coast, we decide to use this. You typically use a server computer to host a database rather than a laptop computer. And then now we have it on Lake Jipe, Lake Chala. Now I've gone full blown. Every fishing area in Lake Jipe, Lake Chala, North Coast, South Coast, Lamu, Zanzibar, in Kisumu Dala, all of them are using this. So now we decide, a popular architecture nowadays is to have cloud services from Amazon, Google, or Heroku host your database for you. So we had GCP cloud service. Now here is where they come in. If you did the GCP study jams, also doing the ML study jams, this can be a very amazing maybe use case for you because you did the GCP stuff and now you're doing this ML stuff and you can use SQL in that because you have BigQuery on Google Cloud that you can use. So you see, you can use all this. Also, Amazon offers amazing stuff. Heroku offers amazing stuff to host your database for you. So we've seen how we can build, let's say, from I'm building, and maybe this is just I'm building something small on my laptop. I'm building for let's say hundreds of users, and now this is for thousands of users. Data streaming in and going out. I'm taking in live data, coming in, coming out, and telling them, giving them points, and all that. So let's now do a small quiz. Let's try to identify if this can be a lightweight or a centralized database. So from first, all of us have used Facebook once. I know maybe right now it's mostly used by millennials and Gen Zs have moved to Instagram, Twitter, and all that, but at least you used it once. So if Facebook's MySQL database holding all user data, do you think, obviously it is centralized. You can imagine Facebook is still the most used social media platform, even though Gen Zs ran away from it, but millennials clung to it. So it's centralized because you are having thousands of users having their data storing their data. And an SQLite database holding an iPhone user's data locally on the hard drive. So okay, now let me suit the audience. Let's also have pixel people or techno people or my very own proud people, my techno people and my iPhone people and my pixel people. So if you're having an SQLite database that is holding, let's say, your call logs or the number of Wi-Fi you've connected in the past 1 week. So that is something lightweight that you can easily hold on to it. And then we have an Oracle database with shopping data from an e-commerce site. So let me use our very own e-commerce site, Sky Garden. So let's say Sky Garden is this e-commerce site that is holding shopping data for users in the past 1 month. So you can imagine how many people shop at maybe Sky Garden in a month with all the amazing offers that they have. So it's probably centralized because this is something that has a lot of data. So I hope now we understand the concept of centralized, lightweight, and lightweight databases. So we now know maybe what you're building and what you're focusing on. So I hope this sparks some interest. We have amazing projects that have been built with SQL and other relational databases and NoSQL databases. I'll just drop a link of one of them. I just saw a tweet before doing this session by one GitHub campus expert called Salim Onyinlola. He's a Nigerian. So you can just check out the amazing stuff they did. I dropped the link in the comment section. And I hope this sparked some interest. It's some minutes to 9:50 and I wouldn't want to keep you. So I see you have some questions in the chat section. Now we can have maybe Ngesa back on stage and Philomena, and you can answer to that as we wrap this up. Hi Ngesa, you can hear me?
Yes, Brian, loud and clear. And
Hi.
what else?
Okay, so maybe I can let me try and read the questions for you, Ngesa.
Yes.
I feel this James Muniu is asking, what are kernel initializers? What are kernel initializers roles in deep neural networks? Yeah.
So what I know is that you can and first of all, kernel is the filter that you're going to run on top of the image. Like the Laplacian filter, another name for it in deep learning is a kernel. And different kernels extract different features from an image. A Laplacian filter, for example, will extract different information compared to a different, let's say another different edge filter. And when you're building a deep learning model, you want like initialize in some way. There's a way that you can initialize them randomly so that you can have them randomly. And also, Keras is going to automatically come up with its own filters. It can come up with, let's say, 32 filters. You can say, okay, we want 32 filters, and then it's going to figure out the kind of filters to use to help you extract the features. So most of the time, it's just a random initialization at the beginning of it. But I was just showing you some key filters so that you can be able to see or understand what's happening in the background. How does this filter run on top of the image, and what do they do when they run the image, and how this entire thing on convolution happens. I don't know if you want to add something, Brian.
Nope, I felt you explained it nicely. Maybe Philomena, you want to add something?
No, I think that was pretty good.
Okay, sure. So let me just check if you have any other question in the chat section. Okay, I've dropped the link to the Discord channel in the chat section, so you can use that. Also, we will try and drop the resources in the Discord channel so you can have them there. Okay, also, we had someone ask about week 2 recording. Sadly, we faced some issues. We changed from YouTube to Google Meet and we were not able to record the session. But as I said, we are always there on Discord to touch on anything. I already shared what was covered on week 2 in the Discord server. So you can head over there and check what was covered. And please do let us know in case you need any question and all that. Any resources or any clarification on what was covered on week 2, sorry. Also, we have James asking, can someone touch on wrappers and how they work?
I haven't really worked with wrappers, but we can discuss it in the next session.
Okay, nice. Also, James probably will drop you an answer in the Discord server. Also, there's someone asking, hello, Duncan Diego. I have already dropped the link to the Discord server in the chat section, but I'll drop it again. So let me just, I just dropped it again in the chat section. Okay. Can you share any libraries used to visualize neural networks?
Yes, we'll share all of them on the Discord channel.
Did you get the question, sir?
Can you share libraries used to visualize neural networks? There's that Vizig or something. There's one called Vizig. We'll share them.
Okay. Also, maybe just to add on this, if you are focusing on visualizing your neural networks in the view of explainable AI or in the view of trying to understand your model, you have ICE plots. You can use ICE plots, you can use sharp values, lime values, and all of these will be covered in our next week session where we'll be focusing on ethical AI and explainability in artificial intelligence. Because what Chungesa has shared, building all those amazing things, now we need to know what feature is actually determining the results of what I'm seeing. Why am I getting this result and how is it happening? So we will cover that in next week's session, which will be on ethical AI and responsible AI and XAI, things to do with all those amazing stuff. We build them responsibly, not just boldly. I'm just trying to check if we have any question. Also, just feel free to drop any questions in the comment section.
I'm just trying to look for my collab. There's some visualization I was doing.
Yeah.
In case I get it, I'll be able to share it before the session ends.
Okay. Also, you can also drop it in the Discord server.
Totally.
Yeah. Nice. Okay. I feel like since it's 6 minutes to the top of the hour, we respect your time and we wouldn't want to keep you any longer. We'll continue the conversation on the Discord server. Of course, we'll be there to respond to any questions. I, Gessa, Philomena, Wayne, Daisy, and of course, all the other amazing community members we have on Discord that are passionate about collaborative learning are there to help you. So, yeah.
Yeah, so thank you, Brian, for all that. And thank you, everyone, for joining this session. It's been amazing. We've discussed deep learning. We've talked about convolutional neural networks, computer vision. We've talked about Keras. And by the way, Keras today is being used by Google, by Netflix, by Uber, by Sun, by NASA, by Yelp, by Square, and a range of startups to build amazing technologies and to solve many difficult world problems. So since we've taken you through all this, your work is now to go and go deeper into what Kaggle is giving you, go deeper into convolutional neural networks, or what they're calling CovNets. Check on how to do the custom CovNets on Kaggle. Check on how to do things like data augmentation. How do they do it? How can you do it? And please go ahead and do all the exercises, finish all of them, because if you do, you're going to get a certificate. And when you get a certificate, please share it with the hashtag of GDG Nairobi, GDG Pwani, and the Mail Study Jam. And from us, we wish you all the best. We want you to learn all these things and next time even share all these things with us. And we also want to thank all of you for joining the session, being with us here since the start of the session until now. And we want to wish all of you a wonderful evening. Good evening. Until next time.